divide both sides by 2 to make it as simple as possible. That's our first step. And in order to determine dw over dt, I would have to divide everything by w. So the numerator is x dx over dt and y dy over dt. And now all we have to do is just plug in the numbers. So let me copy the figure that we had last time. This was w, this was x, this was y. The rate here was 25 miles per hour, and the rate here was 60 miles per hour. Okay. Good. So do we have all these variables? And obviously, I shouldn't say variables, they're functions. So w is nothing else but the square root of x squared plus y squared, because we don't have w. Okay, so let's see what we have. And remember time, we are evaluating when time equals 2 hours. Okay, so how do we proceed? Do we have any of these numbers? Do we have dx over dt?
Yes.
Yes, which is?
25.
Exactly, awesome. Do we have dy over dt?
Yeah.
Very good, that's 60. Now, do we have x? Do we have y? If I have x and y, then I will have w, because all I have to do is just put them in here, square them, and add them up, and take the square root. Keep in mind that we are assuming uniform motion, and time is 2 hours. So this car going this direction will cover x, this car in 2 hours, and this car going in that direction, going south, will cover a certain distance in 2 hours. Considering uniform motion, no acceleration, no deceleration. Can I determine x?
Yeah.
How?
Just plug in 2 for that little equation. 25 miles twice.
Yes, so it's 2 hours times 25, so this must be 50. Good. What about y? So this is 50 squared. Great job. What about y?
Same thing.
Yes, so y is 60 times 2, rate times time. And this will be 120 squared. Let me clean it up and just present the numbers neatly. So 50 times 25 plus 120 times 60. Everything divided by the square root of 50 squared plus 120 squared. That's all we need. And now we can plug it in your calculator. Don't forget to put parentheses around the numerator. Any questions? Parentheses around the numerator. And since the denominator is just one quantity, you don't have to, but I will put parentheses under the square root. So 50 times 25 plus 120 times 60 divided by the square root of, in parentheses, 50 squared. I know what that is, but I'm going to write it like that for now. Plus 120 squared. Close the parenthesis and press enter. So we got 65. Now we have to identify what the measurement unit is here. So what is the measurement unit? Anyone? Measurement unit?
Miles.
Per? Yes, it's the rate of change. So every time we talk about a rate of change, the answer as a measurement unit will always be a ratio of 2 measurement units. So far, so good? Okay, I know we need more problems of this from related rates, so let's look at yes. So let's look at resistance. If two resistors with resistances R1 and R2 are connected in parallel, so I guess there is a figure in the back. We'll look at that in a minute, as in the figure. Then the total resistance R, measured in ohms, is given by. This is a nice problem because the equation is given to us. We don't have to struggle through anything, right? We are given the relationship. If R1 and R2 are increasing at a rate of 0.3 and 0.2 ohms per second, respectively, how fast is R changing when R1 is 80 and R2 is 100? Okay. Would you like to look at this problem? Is this okay? Okay. Perfect. Something connected to physics. So we have, this is problem 35 on 249, and we have 1 over R equals 1 over R1 plus 1 over R2. We are told 0.3 ohms per second, and we are also told 0.2 ohms per second.
Can we zoom out?
Of course. Yes, sorry. So we have to identify what these numbers represent. We're going to read the problem one more time. We're lucky now, as I said, because the equation is given to us that relates these three functions, R, R1, and R2. So let's read again. If two resistors with resistances R1 and R2 are connected in parallel, then the total resistance R is measured in ohms, is given by this. If R1 and R2 are increasing at rates 0.3 and 0.2 respectively. So what do I have to write here? What is this?
R1 is 0.3, R2.
Careful. They are increasing at rates of 0.3 ohms per second. This is a perfect indication of what to write on the other side of the equal symbol. Yes, but I have to mention dr1 over dt. Yes, you're right. So dr1 over dt. What about the other one? Very good. Perfect. Is that clear? If it's a ratio, if the measurement unit is a ratio, this must be a rate. Most probably. How fast is R changing? What am I asked to find? How fast is R changing?
dr.
Very good. When we're given R1 is 80 and R2 is 100. Okay, any suggestions? How do we start? What do we do? Any ideas?
I need derivative of 1 over R.
Exactly. Okay, so what would you do next? Yes, we have to differentiate both sides, but you know me. Maybe you're not going to do that, but I will. What do you think I'm going to do?
You want to get rid of the fractions.
Yes, of course. He knows me too well. I don't like that. I'm kidding, of course. Of course, I'm going to just change those fractions into r to negative 1 Later on, I can do whatever. I don't care. I'm going to plug in all the numbers in the calculator, right? So, but this is easier. Okay, so now let's differentiate. What do we get on the left?
Negative R
Yes,
dr over dt.
very good, awesome. But don't forget raised to -2. So,
Okay.
we bring down -1, we subtract 1 from the power, and then we differentiate the inner function. Excellent. And the same thing for the other two. So it's negative R1 raised to -2 and dr1 over dt minus R2 to -2 dr2 over dt.
Does it flip to mine? Oh, it does. Okay, I got it. Yeah.
Is that okay?
Mhm.
So I am after this and nothing else, but I'm going to change everything into positive because I multiply both sides by -1. Everything becomes positive. And dr over dt is all this, positive, over r to -2. And let's see what we have, and let's see what we don't, and take it from there. So dr over dt, r to -2, r1 to -2, dr1 over dt, plus r2 to -2, dr2 over dt. And we're told that R1 equals 80, R2 equals 100. We are also told that dr1 over dt equals 0.8 and dr2 over dt equals 0.2. All these are given to us. You don't have to write all of them. I was just making a point. So this I have. It's 80 raised to -2. This I have is 100 raised to -2. This I have is 0.3. This I have is 0.2. The only one that I don't have is that. But that's okay. Let's go back. Let's write the equation one more time. And I'm trying to determine R at the exact instant when R1 equals, very good, and R2 equals 100. So here's what I recommend when it comes to this type of equation. So we want to find R, which is 1 over 80 plus 1 over 100, right? So you have to find the least common denominator, etc., etc., etc. If you do not solve the equation like this, but you solve it in that form, that's always easier. So it's 1 over r. The least common denominator is r1 times r2. This needs to be multiplied by r2, and this needs to be multiplied by r1. So the top is r2 plus r1, but I'm going to write it in order. And all you have to do is just flip both. You can do that in a proportion. It's a tiny little trick. So you flip this only because the numerator is 1. Otherwise, there is no need. I'm going to cross multiply. But since the numerator is 1, I flip the left, I get r. I flip the right, I get r1, r2 over r1 plus r2. And this is easier to plug in the 80 and the 100 than to find the least common denominator, etc., here. So then r equals 80 times 100 over 100 plus 80 plus 100. So this is 180. I'll simplify a little bit, and I don't care for the rest. Really, it's not important. Because now I'm going to go back and plug in everything. So our calculation for dr over dt will be 80 to -2 times 0.3 plus 100 to -2 times 0.2, and everything divided by 800 over 18, everything raised to -2. Don't bother with any algebra here. or basically arithmetic. They're all numbers. Just let's plug them in the graphing calculator and we'll get a number. Okay, anything here till we plug in? Ready? Okay, so put parentheses around the numerator. We have 80. Careful with this power. I don't know, I don't claim I know, but be careful because if it's a negative power and if you don't put parentheses, I'm not sure if it's going to give you the correct answer. So be careful with that. You know me, I love my parentheses. Okay, 100 power in parentheses -2. And then come down from there and multiply by 0.2. And then close. And then divide. You have to open a parenthesis. We have parentheses, in parentheses 800 divided by 18. We have to close that, caret, and in parentheses, please, -2. I don't know if it's going to work without. Maybe. So we got 0.1321. So dr over dt 0.1321. And now we need the measurement unit. Can anyone give us the measurement unit for 0.1321? Of course, thank you very much. Indeed. Questions? Questions? So this particular problem was missing one step. The step that was missing is we did not have to develop the equation. The equation was given to us. Okay, ready for the next problem? We can spend the month just on this section. I promise you I'm just going to present 2 more problems and then we can try to finish this chapter. Okay, ready? Okay, so let's look at a situation with a triangle this time. It's an interesting problem for several reasons, and I want to refresh your memory on a different way of determining the area of a triangle. 2 sides of a triangle are 4 and 5 in length, and the angle between them is increasing at a rate of 0.06 radians per second. Find the rate at which the area of the triangle is increasing when the angle between the sides of fixed length is pi/3. So we read this problem and we have an idea of what's happening here. What does 0.06 radians per second represent?
The rate the angle is increasing.
Exactly, like d theta over dt. Excellent. And what are we asked to determine? We're going to put everything in writing in a second. So find the rate at which the area of the triangle is increasing. So we're asked to find dA over dt at a particular instant that cannot be taken into account just yet, which is pi/3. Ready? Yes, Omar, you want to say something?
I'm just not sure I'm following the problem. I'm listening.
Okay. Okay. When we you'll be clear in a moment when after we draw the triangle. You'll see. I'm on page 4. So this is problem 29 on 249. Here's the triangle. We are told that this is 4 meters and this is 5 meters. And we are told that this angle, I'm going to call it theta, is changing, increasing at a rate of 0.06 radians per second. We read the problem one more time before we do anything here. Two sides of a triangle are of length 4 and 5 meters, respectively, and the angle between them is increasing at this rate. Find the rate at which the area of the triangle is increasing. You already told me. Find the A over dt when theta equals pi over 3, which cannot be taken into account just yet. Don't even look at it. It's there because I want to put the book aside, but otherwise it will not mean anything. Okay? So which functions we need to connect with an equation, a relationship? Which functions of time we need to connect through some sort of relationship, preferably an equation?
What would be the area of the triangle?
The angle, the area of the triangle, and
Theta.
and the angle. Excellent. So somehow we have to come up with an equation that connects the area to the angle. Okay. Well, we know how to find the area of a triangle. We know it will be base times height divided by 2. If I consider this the base, then I need the corresponding height. As we know, if this is the base, this must be the height. If this is the base, this must be the height, and so on and so forth. The corresponding height to the base, perpendicular to the base. Okay, so I do have the base, which is 5, but I don't have the height. So let's take a look at this right triangle. And maybe we can come up with the height somehow. Are you okay?
Mm-hmm.
So we need to use the triangle, the right triangle, to express the height somehow. Preferably involving theta, somehow with a trig function. So, any suggestions?
Can you, like, cosine it?
If I use cosine, then I'm involving this piece, which I don't have.
Oh, okay.
I have to involve the opposite of theta, not the adjacent of theta. But you're close, of course. If it's not cosine, what can it be?
Tangent?
You could use tangent, but then I will have a difficulty maybe because I don't have this, right? So again, opposite over the adjacent will not work.
So we're not assuming that it's 5 split directly in half.
Oh no, we can't.
Fair enough.
We
I
cannot.
figured that was assumed by the right
Yeah.
triangle.
So this is a right triangle. So which function will connect the angle and the opposite leg?
Sine.
Of course, yes. So indeed, sine theta equals
H/4.
h/4. Excellent. So then from here I can find h. Can anyone give us h from this equation?
4 times sine theta.
Very good. So then I have now the area, which is base, which is 5, times height, which is 4, times sine theta divided by 2. After simplification, then I have the area equals 10 sine theta. It couldn't be a nicer equation, I hope you agree. So I got these functions of time to be related. I made them related through an equation, a relationship, a link, whatever. Good. What is the next step then?
We find a changing area, so maybe differentiating.
Of
that.
course. So once I have the relationship between the functions, I actually am looking for a relationship between the derivatives, between the rates of change. So all I have to do is differentiate implicitly, keeping in mind that A, the area, and theta, the angle, are functions of time. Perfect. So please tell me how to continue. What do I write?
And the constant doesn't sit outside, is that what we usually go with?
Yes, that will stay waiting patiently.
Then it's cosine theta, and then the derivative. So you done? That's 4.
Great job. And now we need the left-hand side.
It's just dA over dt.
Of course. Good, so this is exactly what I'm after. All I have to do now is plug in the numbers. And we are told, only now I will use when theta equals pi over 3. You understand, I hope this is very clear, but maybe not. Allow me to explain. I hope it's clear that if you replace from the very beginning theta by pi over 3, when you differentiate pi over 3, what do you get? Sine of pi over 3. What do you get? Right, it's a constant. So be careful. You're not allowed to put this in till you find a function called the area. And after you find dA over dt, then you can plug in the numbers. Is that clear? Okay, good. So let me refresh your memory. Anybody remembers cosine pi over 3? That's okay. Here it is, very simple. I'm going to write theta. Sine, cosine. So this is pi over 6, pi over 4, and pi over 3. There are only 3 numbers that we need to remember. And here's how easy this is. One half, one half. So we always start with 1/2 at the top with a small angle for sine. And you end at the bottom for the large angle with 1/2 is again. And this is the square root of 3 over 3. And this is the only angle that has same sine and same cosine. So then how much is cosine pi over 3? Yes. So this is 10 multiplied by 1/2 multiplied by d theta over dt, which is given to us as 0.06. So I'll simplify, and phi is 0.3. Measurement unit. Remember, it's a rate of change. It has to have 2 measurement units, one coming from the top and one coming from the denominator.
What was it measured? I don't remember. It was over seconds, if I remember correctly. Something
Yes.
Seconds.
Yes?
Anybody remember the distance measurement? I think it was meters, inches, what was it? I don't know.
Meters.
It was meters.
It was 4 meters to 5 meters.
Meters a second. Is that meters a second? I guess not.
Very good. It's the area,
Oh, okay.
right? Measurement unit for the top, measurement unit for the denominator. Any questions on this? Well done. Not too difficult so far, right? I mean, some of them can get very hairy. I know that. Okay, should we look at another?
Sure.
Okay, very good. So let's take a look at our third or fourth best friend, particle. A particle moves along the curve y equals blah, blah, blah. As the particle passes through the point 1/3, 1, its x coordinate increases at a rate of the square root of 10 centimeters per second. How fast is the distance from the particle to the origin changing at this instant? The particle moves along the curve. As the particle passes through a point, which is for very later, much later. I don't care for that point. It has to wait. At that moment, its x-coordinate increases at the rate of the square root of 10. I don't care for it. It's at that particular moment. How fast is the distance from the particle to the origin changing at this instant? All those numbers have to wait. I can use the point 1/3, 1. I cannot use the rate of change of the square root of 10 till the very end. How fast is the distance from the origin changing at this instant? We start with a little figure to see what's happening here, and then we'll discuss it. Agreed? Okay, so let's do that. I'm not graphing the function, I'm just giving you the idea. So this is problem 22. on page 249. And we have y equals 2 sine pi x over 2. Well, sine passes through the origin, so I can graph something like this for now. Okay, so here's the particle somewhere on this curve. This is the curve, y equals 2 sine pi x over 2. This is the distance between the particle and the origin. I'm going to call it w again. And any point on the curve must have 2 coordinates. Right? This point must have an x coordinate and must have a y coordinate. And of course, you know what I'm getting at. I'm sure you do. Okay, so can anyone say anything about this? No, you can't. It's just x. But what about this? Can anyone give us that? What is it exactly?
Would it just be that equation there?
Of course, exactly. So this is 2 sine pi x over 2, of course. If x is x, the y coordinate must be f of x. Excellent. So then, can anyone give us anything that we can write that relates what you see here, basically x? I don't have any more information about y, so just a connection between x and w, and keeping in mind that both of them are functions of, that's it. So can anyone give us an equation?
dw over dt.
Oh, we're not there yet. We can differentiate before we get the equation. We have to see the equation first. Did you write it and I didn't see it?
No.
No, we cannot differentiate if we don't see the equation. I only want the equation now. Yes?
W squared plus 2 sine pi x.
Yes. Awesome. That's what I want first. This is our equation by the Pythagorean theorem. The longest side squared, which is the hypotenuse squared, equals the sum of the legs squared. We agree with this. Okay, perfect. Now let's clean it up a little bit before we start differentiating. So I'm going to write w squared equals x squared plus 4 sine squared pi x over 2. Do we agree with this step? I have to square 2 and I have to square sine. Is that okay?
Yes.
Okay. Remember w and x, one more time. I know I repeat myself a lot. W and x are both functions of time. Okay, I don't want you to forget that. Good. So now we are ready to do what Colio is already telling us to do. He's bossy. Just kidding. Yes. We are supposed to? Yes. We're supposed to differentiate both sides. Good. Can anyone give us the left-hand side?
2w.
Yes?
2w dt.
Excellent. Great job. The right-hand side.
2x.
Yes.
dx over dt.
Very good.
Let's see.
Plus.
Plus
Yes.
2 sine. Would it start off with 2 sine?
Yes, but we have to multiply by 4.
Then we get rid of this is 4. I can start the problem still.
Yes.
Alright, so it would be 8 sine.
Pi x over 2 times.
Times cosine
Yes.
pi x over 2.
Very good.
There's no way around
Times.
that, is it?
Say it again.
There's no way around pi squared.
The-
Quotient rule, is there?
No. So you have to differentiate this.
Okay.
What is it?
So it'll be, they're
differentiate the first one, so.
No. This is just the constant times x. Pi over 2 times,
dx.
very good. Is this clear? Let's do this one more time. So we bring down 2, and we subtract 1 from the power. 2 minus 1 is 1. Now we differentiate the inner function. Now we differentiate the inner function. Now we differentiate the innermost function. Is that okay, everyone? Clear? Okay. So what are we after? This is what we are after. Okay, so I will divide both sides by 2 and also by w. And my cheap markers are complaining. No, this is just fell on my. I got it. Maybe not. I got it. Okay. So dw over dt, w in the denominator, I'm simplifying by 2. I'm simplifying by 2. I'm simplifying by 2. I put pi over 2 in front, and I can even simplify again by 2, but that's okay. So we still have sine pi x over 2. We still have cosine pi x over 2, and we have dx over dt. Okay. So now we know that x is, so the point, I didn't even write it. The point was, what was it? 1/3 comma 1. So x is 1/3, y is 1. And we're told that the x coordinate changes at a rate of the square root of 10 centimeters per second. What is the square root of 10 centimeters per second? Should I read that sentence again?
Yes, I was impacted.
Yes, okay, let me read it again. As the particle passes through the point 1/3 comma 1, its x coordinate increases at a rate of the square root of 10 centimeters per second.
So that would be dx of dt.
Thank you very much. Indeed, dx over dt. So now let's see. I have x, 1/3. I have dx over dt, the square root of 10. I have here dx over dt, the square root of 10. And what about w? I don't have w, but I know that w will be the square root of the initial equation. I'll get to it when I'll get to it. But I have to go back for a second and determine sine. How much is pi over 2 times 1 over 3? Pi over 2 times 1 over 3 is pi over 6. Okay, sine pi over 6. 1/2. So this quantity is 1/2. The same thing with pi over 3. Pi over 2 times 1 over 3 is pi over 6. What is cosine pi over 6? Yeah, the other number. Perfect. So this is the square root of 3 over 2. And now I have what I need here. So this will be the square root of 1 over 3 squared, which is 1 over 9. Sine pi over 2 is 1/2, but squared will be 4. So plus 4 times 1 over 4. That was 1/2. We squared is 1/4, and then 4 in front. I'm going to write everything one more time because it looks messy. So 1/3 times the square root of 10 plus, I will simplify 4 and 2 now. So I'm going to say 2 pi times 1 over 2 times the square root of 3 over 2 times the square root of 10, and everything over the square root of 1 over 9 plus 1. So I cleaned it up a little bit, And now we're ready to plug it in, the graphing calculator, and get the number. So now, what would be the measurement unit of this answer? It's the rate of change of distance from the origin to the particle.
Just meters per second.
Centimeters per second. Yep, excellent. Good, ready to plug in the numbers? Okay, let's do that. Careful with parentheses. Doesn't want to turn off. Okay, so we're here. Left parenthesis, 1/3. In parentheses, 1/3. If you want to do that, you can put just simply the square root of x over 3. It's possible. It's fine too. Okay, so a 1/3 in parentheses, the square root of 10. We can also factor out the square root of 10. Okay, I didn't put parentheses under the square root. Okay, I think I can live with it for now. 2 pi times 1/2, I'm just going to put pi because I simplified again. And then I will put in parentheses the square root of 3 times the square root of 10, which is the square root of 30. Close the parenthesis, come outside of the square root, and divide by 2. There is another 2 in there. And then I divide by the square root. And in parentheses, 1 divided by 9, and then plus 1. Close the parenthesis and come outside. And enter. 9.2161. Can anyone confirm? So I put 1/3, yes, I'm the square root of 10, yes, plus 4. I put 2 pi, oh, yeah, no, I was looking at the top. Yes, so 2 pi divided by 2, so it's pi, yes, correct. The square root of 3 times the square root of 10 is the square root of 30. And I still have to divide by 2, yes, okay. And then divided by 1/9 plus 1. Can anyone confirm the number?
That's what I got.
Okay, thank you very much. I trust Paige, so I don't have to check again. Okay. Do you think we feel okay about related rates? Do you think we should look at another example? Okay, we can do more problems at the end, so let's try and finish 3.10. 3.10 is half done, and 3.11 I need 10 minutes, actually.